See, it's time. Can you see my screen? Everybody see the screen okay?
Your timer.
Yes.
Yeah.
Yep, the timer's there. Okay, so it's ready to begin. Welcome to another exciting microcontrollers class. I've got a couple of things that are on my list of items to cover. First and not least is the homework. We got a homework due today. And it was pointed out to me that I had forgotten to check a checkbox that allowed others to see it, even though I was under the impression that you guys had seen it since last week. So that, bummer. But it's not a particularly difficult homework, and we have covered it in some detail. So what I'll do is I'm going to kind of go through it. And you guys can ask me questions if you want. Otherwise, I think it's going to be pretty straightforward. We've already gone through these things with a pretty fine-tooth comb in the last lecture, which is recorded in case you want to review it prior to completing this, the homework. So I'll just sort of scroll through it. You get 2 stabs at it, like always. It's graded by computer. It's really about I2C, which we used for the real-time clock. And, well, I guess we've covered SPI, I2C. We haven't really covered serial ports yet, so that's my next topic, which I plan to do. I did want to do Ethernet, and I might be able to do a couple of demos on that. So at least we'll see some demos on how you can do Ethernet with the Arduino, even if we don't get a chance to do a hands-on thing with the Ethernet, which I kind of would have liked to have done. So are there any questions about homework 9? It's due tonight. I'll just sort of scroll through it again. You guys know about I2C at this point. Simplex, local area network. It's a bus. It's a network bus. It's a network. It's a bus. It's a network bus. Or maybe it's a bus network.
Is it asynchronous too?
No, it's synchronous, right? Because there's a clock.
Right. Okay.
So we have one clock line and we have one data line, and we're sharing the data line just the way we did in the lab yesterday. We were sharing the channel with all the NRF24L01 transceivers. So when people started to broadcast at the same time, we stepped on each other's packets. That when you have a media access control layer, what you do is you sense the carrier of somebody who's already transmitting, and you wait for them to finish, you see. So this is what happens if you are if you're a pilot and you're using the radio. It's really good if you wait for air traffic control and the other pilots to stop talking before you start to talk, because when everybody starts to talk at the same time, nobody can understand anybody, and it's a very poor way of communication. So what you do is you adopt a standard radio phraseology, which people are able to become facile with, so that they can basically use a protocol so that all people who are on this so-called party line can communicate efficiently. And so that's typical. So we didn't do that. We just started talking all at once. And I thought that was a very educational thing. But if you were to take a look at, for example, the Aloha network, which is a packet radio network that dates from the 70s, 71, in fact, they were doing exactly the same thing to hook a whole bunch of nodes to a mainframe on the Hawaiian Islands. They couldn't run wires. They had to use a packet radio network. And as a result, they came up with a media access control protocol, which was the predecessor to the Ethernet. And so this was basically an invention, and it was done by Abrahamson and Kuo. And they effectively devised a means by which teletypes, they say using RS-232, but in fact it was using a serial current loop could communicate. And so this is a system which is in use today by ham radio operators. And so this is if you're I happen to be a ham radio operator with a packet radio modem. If you're trying to modulate so that you can basically use the voice band in order to be able to communicate digital data, you need some sort of a modem that's going to essentially be like a phone modem that works over the radio. And then you have to worry about a whole bunch of people sharing the same phone line, like a party line. The mathematics is ignorable. Forget about the mathematics. If I go through it, well, trust me on this, it takes 2 weeks at least. And in fact, you could do a whole semester on the mathematics behind queuing theory, which is really what this is about. And we can cover some of that in communication systems. So there's a what you might call an application for probability with random variables in there. And it makes a certain number of assumptions about analytic arrivals and processing time and blah, 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 blah. It goes on and on and on. If I tell you all about it, I'm going to sound like Charlie Brown's teacher, right? You're going to hear, and you'll just, your eyes will glaze over. So then that's that, the Aloha network. And we were kind of on the cusp of reinventing the Aloha network yesterday, which was kind of an exciting thing. The other thing that happened, is a little bit of a blemish in the for the remote students. It can be a big blemish, and that is Laboratory 11 for those who couldn't attend, because I'm doing separate labs for those who can't be there. And if you can't be there, I feel bad because you're missing out on an interesting hands-on experience, but you can still have a hands-on experience. And so what I did was I devised the Lab 11 for those who are on the ground and able to come to class. And then I devised a separate lab called Lab 11 for remote learners. And I'm calling it Sign Me Up. Clever, right? So what we're going to do is we're going to do a little passive filtering on the output of a PCM generated square wave. And that passive filter is going to take that square wave and make it more like a sine wave. And so what I've done is I gave you a link that you can click on. And when you do, if you have an account on Tinkercad, what you'll get is the classic means of generating tones using PCM on the Arduino. Let's start with the demo, and then we'll go through the explanation on how it works. Because if I do the explanation on how it works, your eyes will glaze over, but if you hear the demo, maybe it'll all come through. So what we'll do is hit start, and then I'll move the microphone over a little so you can hear this wonderful sound. Were people able to hear that okay?
Yeah.
Yeah.
So
okay.
by changing the pot, you would be changing the frequency.
That's exactly right. And in fact, there are limits to what this simulator can do, because I have a feeling it's going to work way better on your computers than mine. And if you did this with a real Arduino, it would actually sound good. But when you do it with the simulator, well, it sounds bad. Anyways, it sounds what it sounds. What we're doing here is quite simple, really. We're reading from the analog input. We're normalizing the analog input, which goes from 0 to 1024, into a variable that's we're calling a parameter, and that parameter is t, and then T is being used to create this this tone, and so we're essentially, how do you say, um, modifying the signal a little bit with T. So that's it. And what I wanted to do was I wanted to have you guys do a filter. And if you look at this article under Making Waves in Nuts and Volts magazine, you will find a passive low-pass filter, which is done in 4 stages. And there it is. And I thought, wow, wouldn't it be fun if you guys could implement this little passive filter using Tinkercad? We'll take the input from the output of our little PCM, and then we can add a little oscillator to see how the different taps look. And I would expect something similar to this. It starts to rounds things off a little bit more, and then eventually you'll get something that kind of looks like a sine wave. So basically it'll take the square waves being output from the Arduino and convert it into sine waves. You could certainly do a course on filter design, but I'm not going to do that with you guys because I think such a course takes 15 weeks and we're just going to get a little, I'll call it hobbyist type experience by implementing the circuit. Now, lest you be overwhelmed by the process, what I would do is show you an example. Sorry, was there a question? So anyway, here's a low-pass filter with a function generator that I threw together earlier today. And what I did was, instead of using the Arduino to generate the square waves, I used my little function generator over here. And then if I click on tinker this, that sounds like a rude thing to tell somebody, tinker this. And you point at a rude place. Like, what? So then here's what it looks like before and after the square wave hits the little low pass filter. So here's a little capacitor and a resistor. If you stop this, you can click on a resistor and you can change its values. Here the resistance is 1 kilo ohm. You can click on the capacitor, change the value. Here it is 1 nanofarad. Well, you can certainly
100 nano.
100 nano, so you can change that, make it, 100 microfarads and see what happens if you like to do those sorts of things. So then, now it looks more like something else.
It's a triangle wave.
Yeah. In fact, you could probably put a triangle wave in and see what that does. Now it looks like a sine wave. So if you ever got it to the point where there was a triangle wave, one more low pass filter would kind of turn it into a sine wave. There's also a way to change where the output is going. And you can do that here. Let's see if I can get that little doodad out of the way. Oh, I see. He wants to be in the way, doesn't he? There. So let's put this in here. And then you should also be able to change frequencies. I don't know if you guys can hear it. I'm going to hold the microphone up to my little speaker here. Hold on. Now, you know that's not a megahertz, right? Because not even dogs can hear a megahertz. So there's something going on here with the simulator. When it thinks that's what a megahertz sounds like, you know there's something terribly wrong. Let's see if we can get this down to something we can hear. I have no idea why it stopped producing sound, but you can see the oscilloscope doesn't agree that the sound has stopped. Maybe it's really resonating with this in the simulator. I don't know. Anyway, let's stop it for now. So you can kind of see how it's possible to construct the before and after picture with the oscilloscopes. You can certainly use function generators to test these things, but I encourage you to use the Arduino and its output. And the other thing I was tinkering with, it's kind of fun to tinker with this stuff. It's too bad it's the simulator and it's not 100%. There's a, let's see if we can get this one to work. This one is supposedly inductors with resistors and capacitors. I think that's too complicated by half for you guys. Just stick to the design as presented in nuts and bolts. But you can see that you can get, I don't know if you can see this. I can't zoom in. I got to tinker it before I zoom in. But in any case, these little brass areas look like little curly inductors. So that's cute. And you can click on those things and change it if you decide to use inductors and capacitors. Then, if you really want to get fancy, you can do an active filter. So this is a first, second, third, and fourth order filter that's active. And if you guys are into active filter design, I mean, this is pretty cool because you can see what happens after each one of the stages. See how the waveform progresses. I find it terribly tedious watching the simulator propagate through all the stages until it settles down, because it takes like a couple or 4 minutes to just kind of settle down and do what it's supposed to do. So I don't really care for this kind of simulation because I find it, I don't know, too antiseptic or something. And besides, I don't really want to get you guys too bogged down with analog filter design, because that in and of itself is another 15-week course, which we don't need to do. So here's a simple low-pass filter. It's just a resistor and a capacitor with a before and after, but it's very similar to what we saw before with the little slide switch. So it's not very educational to show you this. But what I can do is I can say, you can sort of see how these things come together. If you want to just add more resistors and more capacitors, you can build yourself a nice RC network. And I thought that would be kind of a fun thing to do, and it still gives you a hands-on experience. So working with the simulator is a little bit tedious, but hey, what can you do? Some people are doing work with EKG, and this is an EKG amplifier, which I thought was really cool. Now, you can, of course, buy these things, and they're not terribly expensive, and you buy them as an Arduino Shield for like 20 bucks or so. But I think it's nice to be able to simulate this. Someone asked me, I have an EKG project for my senior project. Do I need more bits? I'm like, no, you don't, right? Your output is like a millivolt, and you're way below the noise floor, right? Because 10 bits is 1023 levels, and it goes 0 to 5 volts. So 5 divided by 1024 is like 4.8 millivolts. So a 1 millivolt signal is like noise. This thing can't digitize it. You don't need more bits. You need an amplifier. You know, and it's a funny thing. You talk to these people and you think, oh, geez, they took the microcontrollers course, therefore they know how to digitize everything. But they really don't, right? Because, well, the world isn't 0 to 5 volts. It's just not. And the signals that come off your body are really low level electrical signals. So if you want to play around with that stuff and amplify it, you need things like this, which is, I don't know, perhaps 5 op amps, and amplifies an very low level millivolt signal. And in fact, you'd want to do this so that it could filter out the various waves that are embedded inside of an EKG, the PQRST waves, that sort of thing. So as a result, it's kind of fun to be able to do the mixed signal simulations. And that is one thing where I think Tinkercad kind of shines. It's too bad it's not a more accurate simulation, but it's an interesting one. So it's worthwhile playing around with that stuff, I think. So that's my overview of the lab for those individuals who are interested in doing it remotely. It's not a particularly complicated lab unless you really want to understand what's going on with the multi-stage filter design. And then in that case, well, I can give you the intuitive idea that this is a low pass filter, but it has a cutoff, and this is another low pass filter, and it has a roll off, which is going to start at the same place as the prior one, but it'll continue to emphasize it. And each one of these represents another attempt to take out some of the high pass signals.
So
And I can, yeah.
this would make a sharp dip, right?
Well, the problem is that the sharper the dip you get, the more distortion you get at the knee of the filter. So if you were to build a filter that essentially just took out 19 kilohertz, which is very typical for FM radio because 38 kilohertz is the multiplexing tone between the left and right channels. So you try and take out the 19 kilohertz pilot tone so that people don't hear it. That notch filter has to cause a distortion if all you want to do is take out 19 kilohertz and not 1901 kilohertz or 19 or 18.999 kilohertz. So doing that sort of thing inherently causes all kinds of interesting, we'll call it Gibbs phenomenon, which is a what do they call it? An ODE, an ordinary differential equations thing that you can study, and effectively causes a lot of phase modulation in the waveform because you're getting closer and closer to the cutoff frequency. So typically what happens is we say something like, oh, well, people can hear from 0 to 20 kilohertz. We're going to sample at 44.4 kilohertz. That's typical CD audio, which means we can have frequencies that go from 0 to 22 kilohertz according to Nyquist, but we can only hear from 0 to 20 kilohertz. So what we do is we start our cutoff at 20 kilohertz and we finish it at 22 kilohertz, because what happens there is we need to roll off the higher frequencies gradually.
Oh, that makes sense.
See, because if you do it too quick, you get all kinds of distortions, and it doesn't sound good. It'll just distort as you get up into the higher frequencies. So giving yourself that extra 2 kilohertz of headroom in bandwidth is really critical when you go to design the system, because Nyquist is a theoretic thing. It's not a practical thing. So when somebody says, like NVIDIA, they'll give you a general purpose graphics processing unit and they'll say peak performance is, make up a number, 16 gigaflops per second. The guarantee is it will never go faster than that, because that's peak performance. So what you'll get is, your mileage will vary. So that probably means you're not getting anywhere near 16 gigaflops per second. But it's nice for the salespeople to say it, and maybe they can even make a demo that actually gets close to that. But they're professionals and they spent all year doing it, and now they got this one thing that does it. But if you're not doing what they're doing, you're not getting it. So that's my sort of spiel about these sorts of limits. Right? Theoretic limits are just that. They're theoretical, not practical. But you knew that already. It's intuitively obvious, I think. So one of the things that I wanted to be able to do, and I'm going to give you a quick demo on this anyway, because I think it's sort of a fun thing. If you take I don't know if you've seen these or not. I'm going to show one to you real quick. You can get an Ethernet shield, and we have a number of these. See if I can get you some nice pictures. Yep, there they are. This slaps on top of your little Arduino, and then you can plug Ethernet into your Arduino. So this is your Ethernet interface for your Arduino. And yeah, they are a little expensive at $13.59. But when Radio Shack was going bankrupt, I was going from one Radio Shack to the other, buying these things at a discount. So I got them so cheap, I just had to snap them all up. And they were like a couple bucks a piece or something at the time. So I said, man, what a bargain. I can't run away from this. I'll use them in my class. So I got a whole bunch of these things, and that's really cool. and now they've gotten back up in price. And well, I guess we've all missed our opportunity to buy cheap Ethernet shields.
You didn't.
But I didn't. I was there. I was on top of it, and I jumped right on top of that stuff. And I thought, well, I really want to have Arduinos on the internet because it's the Internet of Things. And you don't get the Internet of Things unless you get on the internet. So we had to be on the internet. We had to have our Ethernet shields. Of course, it's actually to your advantage to do this when you're home because you have, well, system admin rights over your own network. Nobody should be able to complain if you plug something into your network, right? Especially if you're writing the program. So here's a little program that I used to do a telnet server. Let me get the audio here going. First port potentiometer is on analog input 2. The other one's on analog input 0. Analog input 1 is being used for audio. And what we're going to do is telnet to the Arduino. And he's outputting the X and Y coordinates of the two potentiometers. And here you can see as I turn this potentiometer here, the output streams the changes out to the console. And in fact, I can diddle this other potentiometer here and change this potentiometer and get two different numbers. So I'll change one and I'll change the other, and we can see both potentiometers can change the output. And so there's my X and Y output coordinates, and certainly you can use those from an arbitrary program that can read from the console coming from a telnet client. Hope you like my little demo. Thank you. So I thought that was pretty cool. So telnet's one of the protocols you can use, and then we've got another one in here where we've got the Seed Studio Ethernet Shield. That's the one that we have so many of. Let me see if I can get that video to run.
So how do you stream it? I don't understand it.
Well, what it's doing is it's printing out to a socket, and Telnet, it gives you a socket. Then you can have an input stream and an output stream, which is just an unformatted sequence of bytes, but it so happens the bytes represent characters. So when you do the print, it's just like printing to the serial port. Effectively, you're printing to a socket. So it's an output stream, just like printing to a file or printing to the console.
So could you design a receiver to receive that information, or?
Telnet is a receiver, right? I mean, it's a transmit. We're using it to do Telnet protocol and transmit to the Telnet client, which is receiving the data. Now, if you wanted to open up a Telnet client, let's say in a different language, such as C or C++ or Java or Python or C#, then the Ethernet becomes your substrate about which you can plug in a whole bunch of different items, and then you can communicate to those items. So if you have a soft dial on your graphic user interface, you can stream in the other direction too, and you can stream towards your Arduino. And I can give you some examples of that as well. So that's a pretty cool thing, because being able to stream to and from the Arduino is kind of a compelling argument. I mean, you want to be able to do that sort of thing to get the data in and out. It could be audio data, or it could be digital data that gets downloaded into the wavetable of your DAC, and then you can send that out to the speaker, which is another thing that we tried doing. So I'll give you another demo and you'll see.
Okay.
Hi, everybody. There was a question about whether or not the Seed Studio shields work the same as the WizNet shields from DF Robot, and I'm here to tell you they're identical. You can try and see what happens when you crank down your assisted power supply. They're drawing a lot more power. Now they're drawing 140 milliamps, and look what happened to their power supply there. This thing here, it looks like it might still be working, but when you go back and you check, it says client disconnected. Let's see if it comes back, and it does. So it's drawing more power, but it is otherwise compatible, pin for pin compatible with the DF robot shields. Thanks. So therein lies a warning. If you try and plug these things without any kind of power assistance, they draw so much power they can basically take down your USB hub. And so a lot of times what happens is we take the fact that we can power our Arduinos off of the USB from our laptops for granted. And oftentimes during a debug session, I'll plug in an adapter because I'm afraid that maybe we overloaded the USB output from somebody's laptop and things don't work properly because of the power issues. Well, at some point, somebody said, you know, these Seed Studio Ethernet shields, which I got for cheap from Radio Shack, aren't working. You got a bargain, but it was broken shields. And I'd say, yeah, but they were really cheap. They say broken, broken, broken. And I'd say cheap, cheap, cheap. And so then they'd say, well, we can't get them to work. And I'd say, well, you got to plug it in. And that's the deal. And so once you give it enough power, it works fine. So that was part of the, the Seed Studio versus the WizNet power draw argument, because WizNet is a custom chip that came with a cheap shield. And then there was the Seed Studio shields, and they seemed like they weren't working, but yeah, they are. Let's take a look at the WizNet power draw. This is kind of an interesting experiment. Hi, everybody. Just wanted to show you my Arduino is active and is updating the web page. In order to do this, I had to put a power supply on the Arduino using a WizNet board. You can see my Arduino is not drawing any current at all, and I'm being able to maintain 5 volts. Watch what happens, the voltage, when I turn off the wall wart. It starts to draw 110 milliamps, and the voltage drops to 4.90. That's bad news. When that happens, I get a client disconnect, and the WizNet chip is working, but just barely. We're right at the margin of what is permitted. So if we got plenty of power on the USB, things are still working right now. But plugging it into a power supply might make a lot of sense to get things running. Watching the voltage drop like this is not a good time. I'll turn on my power supply again so you can see what's going on. And we're back up to 5 volts. And things are fine here. Now you throw a stepper motor on there, and you're really going to be powering everything at the margin. Just thought you'd like to know. Thanks a bunch, boy. So there you have it. You know, that's proof positive. These things take power, and you'd expect that, right? But maybe you didn't realize just how much power. Now, some hubs, and I have a couple of hubs on order now, will actually give you a 1.5 amperes in the front, because they're meant for both driving data and for charging. And so if you have data coming in and you decide you want to plug in your cell phone or something for a charge, they'll recharge the cell phone, although most people wouldn't like to use their hubs for charging. They have special hubs for that. So from the point of view of the Arduino, we have what I would call a suite of internet-based Ethernet tools. And that suite enables us to do all kinds of interesting things. And you can gain access to that using the Sketch import library. And what you do, and you can see this, I've already installed it, so it won't be particularly interesting here. But if you go to the Include Library, Manage Libraries, and you type in Ethernet, you'll get a whole bunch of choices about the stuff that you can install. My library manager appeared on a different monitor. Hold on. It's not responding. Oh, I got a dialog box here. See, it wants me to do an update, but this guy, My modal dialog got hidden. Manage libraries. I do have a more modern version of the Arduino IDE, but I started the old one instead because of randomness, I guess. Ethernet. There. So here you can see my built-in Ethernet has been installed. There may be others in here which I've also installed. And after having done that, if I go down to the examples, you can find there's a bunch of Ethernet stuff. And you saw the Telnet server. You can do a Telnet client. There's a web server which you can run. I've run that before. That's fun. Once you have a web server, you get a web page, and you can interact with the web page in order to be able to control things like a stepper motor. And that's a good time too. And we already know how to do stepper motor stuff. And when it comes to doing like the web page, what you're really looking to do is run a socket server, wait for an accept on the connect. And then once you accept that connection, you dispatch it by gaining access to the input stream and the output stream. Once again, the web server appeared on a different monitor. Not entirely sure I know why. You can change the IP address so it's compatible with your local area network. Plus, you can change the MAC address. Oh, that's particularly dangerous because now you can have a whole bunch of things with identical IP addresses and MAC addresses. And if you plug into the campus network, oh my God, it'll wreck mayhem. With identical MAC addresses and IP addresses, I think the security people will come running or something. So once you've got the client connected and you've got some sort of available data, you can do the read and get the data that comes in from the client and maybe write it out to the serial port. And then to the client, you can do the print line. So this is how you do your streaming. And so what you can do is you can stream out the text that would normally be sent if you were speaking HTTP protocol as an HTTP daemon, which is also another name for a web server. And so what you'll do here is you can put in the analog input, but what I would do is I'd put out a form, and that form would give the user the opportunity to enter in a number for something like how far they want to advance a stepper motor, or where they might like to position a robot arm. And so you can have two-way communication over the Ethernet with your Arduino. Not bad for an 8-bit toaster controller. I mean, if you had a toaster, what would you want to do with it? And I'm like, well, let's make a reflow oven out of it and put it on the network. Right. That's what you do with it. So, there's all kinds of things. Once you add a computer to something like a toaster with an Ethernet interface and all these other things, the sky's the limit on how much value you can add to that toaster. Because once you've taken a $26 toaster and added all this stuff, you've turned it into a $450 reflow oven, which is cool if you want to sort of reflow boards. Do people know what reflowing is?
Could you give us a
Yeah,
brief?
so reflow is what you take a little solder paste and you plunk it on top of a printed circuit board and you heat it up until it starts to flow. Here, I'll show you. Reflow oven.
You mean it like solders things for you?
Yeah, essentially, this is actually, they're so terribly inexpensive. You probably wouldn't want to make your own, but I have. And happy buy reflow oven from AliExpress. Well, this won't burn down the house, will it? So yeah, what he does is he basically gives you the ability to control the amount of heat that goes into a printed circuit board that's been covered with solder paste. And presumably after you cover the board with solder paste, you do the pick and place of small surface mount components, and they go on top of the pads. And then once you put that in the oven, it heats to the point where all the solder melts, everything gets fixed into place, and then it cools. And so in effect, you can make your, in this case, prototype surface mount boards. And so this is a terribly inexpensive, it says infrared IC heater desktop reflow oven. God, I
Is
want
there a
one.
video of someone using this or something?
I would think
Probably.
so. Oh, tons of them.
It'd be
So,
cool to see how it works because I've never seen this before.
oh yeah, there are places where you can get this done in an assembly line, so that the boards get chugged out like chiclets. Let's see if we can get a reflow oven. How about a desktop reflow oven in action? Well, reflow in action. There, reflow in action. So what do we have for videos? Oh, here it is. Convert your toaster oven. I actually did this. There's a board you can get called Reflow Leo, which is a Leonardo and a little LCD display, and it uses a K-type thermocouple, which you drill a hole through the back of your toaster oven, and it measures the actual temperature in the toaster oven and controls whether the toaster oven is on or not. It's a how you say bang bang control, right? Because now this guy doesn't look like he's got it under computer control. So he's just taking whatever device he's using and he's going to throw it in there, and then it'll get nice and toasty, I should imagine. Let's see. Doesn't he oh, maybe he does have a temperature sensor. Let's see if we can do this full screen. Now that is measuring the amount of power the toaster is consuming, but it's not controlling the toaster. So he's pulling 1200 watts now. But that's typical for these kinds of devices. And you want to be really careful not to overheat the PC boards, or else they'll get nice and toasty and they'll turn colors and everything. And it looks like, yeah, he's instrumented the toaster, but he's keeping an eye on it. So I don't know how the control is being effected. Here, 3 minutes later. And now he has his little, there it is, surface mount devices. Gotta love it. Looks like he's got a bunch of LEDs on there. Not a particularly impressive board. He's not making computers, but it doesn't matter. You get the idea.
So that, what happened there? I don't get it. How did he solder this?
The solder paste was placed on the pads, and then the pick and place was done with tweezers. And then he put the whole thing into the oven, and the solder paste melted.
So solder paste is like different from soldering wire and stuff.
Oh yeah, solder paste is not the same as solder wire. Okay. Solder paste is something that you can buy, and usually it's little solder balls embedded in flux, and you get a little needle, and you can apply them one little dab at a time. And then you can get them in lead acid, or you can get them in lead free. I prefer lead acid because the melting point is a little bit lower. And typically it has a limited life. So after about 6 months, even if it's in the refrigerator, it goes bad. And when it goes bad, you can't even squeeze it out because it's solidified. And then,
so when you heat it up, it goes solid. Is that what you're saying? Like after you heat it up?
That's correct. It's like it's a third-party alloy, which, well, it's a third alloy. Third meaning, well, let's say you've got the copper pad, you've got the components material, and then you have this third alloy with the low melting temperature. And when it melts, it's conductive, but then it solidifies rather quickly. And then what you do is you basically have the ability to solder those devices, which are generally smaller than the eye can see comfortably without some sort of optical assistance. So, for example, when you look at the world of surface mount devices, SMD wiki, you'll see there's 0402, and there's 0201, and the sizes are getting so small that, well, you can kind of see what's going on here. Things are getting very tiny. And this little device over in here is probably going to desolder that little capacitor. So these are little hot soldering irons running in tandem, and they're going to pull that little surface mount capacitor right off. And you can see why it's so difficult to do the soldering, because when you look at something like this, you can see These little guys are tiny. And usually what you do if you're trying to solder by hand, something like this, is you would use what's called drag tip soldering, where you get a special soldering iron which has a concavity in the tip. You fill it with solder and then you drag it over the leads. It's very easy to bridge the two leads and cause a short circuit. But if you wanted to do it upright in production, you get a stainless steel stencil along with the printed circuit board. Then you squeegee on your solder paste just enough to go through the thickness of the stencil. And then you do the pick and place operation on all of the surface mount stuff at once. And then you chuck it in the oven, give it a bake, and then the reflow occurs, and you've got yourself a completed board. In the production world, what you want is you want an assembly line that essentially includes a pick and place machine and a reflow oven phase. And once you have that, and this is a classic example. See these reels? These are reels of components. We have these reels in the stock room. And you mount these on a pick and place machine, and it grabs off the parts that it needs and shoots them out like machine gun bullets onto already prepared printed circuit boards that have the solder paste already applied. After the components have been placed on the board, then you want to run them into the oven. Then you do your your automatic optical inspection, or AOI. So what that does is it looks for errors in the bridging. Like it's very easy to get two solder lugs that are next to one another and have them bridged together. So these pick and place machines, you got to keep them running smooth and running them correctly. Plus, they're terribly expensive. So if we're doing pick and place in house, we use tweezers and a microscope. That's what I do anyway. And usually that's okay for a small, prototype or even a tiny pre-production run of, let's say, 10 boards or less. And so when you look at the shields that we created for the DSP work, the audio shields, there's a single SOI8 small outline integrated circuit with 8 pins that uses that's the heart of the board. It is the 4921 microchip digital to analog converter. The DAC essentially is a surface mount device, along with a couple of capacitors and that sort of thing. And so when we do a mixed board, and that's what you look at when you look at that board, is you're seeing a mixed board. You see two kinds of components: surface mount components, which can be automated very easily, and then automated for assembly very easily. And then they have the through hole, and the through hole is a terrible pain because you're soldering that by hand, and Chris will tell you because he was helping solder during the summer.
I saw.
Yeah, it gets tedious after a short while, especially when you're doing 10 or 20 boards, and I don't know, there's probably 4 through-hole connectors, the mezzanine connectors.
Yeah, with the mezzanines, it was over 50 connections aboard.
Yeah, I was just trying to do that computation, but it sounds like you did it already. So that's right, and that must have taken you a long time, I would think.
Yeah, it took like 30 to 45 minutes aboard at first, but I got faster by the end because I had a method.
Cool.
Muscle memory.
That's cool. Yeah, what method did you use anyway? You just sort of set things up properly?
Well, I marked like a old breadboard with where to stick the pin headers in, so I could just like stick pin headers in a breadboard and then just set them right on top of it.
Yep, that's the way to do it.
A lot of time, like figuring out where they go every time and getting it set up, and so I could just get them set up in a quick second and then just start soldering.
Cool. So yeah, with those boards, you had 0603. I wonder if I can zoom in on this. 0603 capacitors, and the smaller ones are 0402. Now we happen to have an 0603 capacitor bank, which gives you a great deal of variety in the 0603 world. And you can look at those capacitors and they are tiny. I don't think we have any 0402s in the house. That's my limit. I don't do that. At 0.1 by 0.1 millimeters, that's small. I mean, that is tiny. I keep two kinds of microscopes handy. One is a binocular optical microscope, and the other one is a USB microscope, which I use for display work and recording. And if I, if I really get into this stuff, I'll also keep my very, very powerful reading glasses on. You can go to the store and you can buy 2s, 2.0s, 3.0 reading glasses. But if you go on eBay, you can find 8.0 and 10.0 reading glasses, which are really kind of like, I don't know, jeweler's loupes. And I also have a jeweler's loupe, which goes to 10x and 25x. So you're kind of putting microscopes on your eyes when you're doing stuff like that. And it gives you a lot of eye strain. So you got to kind of watch it. Microelectronics has not gotten hobbyist friendly. I'll put it that way. It's tough to work with things like this. I mean, that's not easy. When you make a mistake with this, it's not going to give you a syntax error, right? It's just not going to work, right? These little guys, if they have a solder bridge, you're going to be sitting there with the microscope going, I wonder where the error is. And you're going to be going through this and you're going, wow, this thing got really hot. I wonder what happened. And then you'll be like, oh no, I've ruined the whole board. And that can happen. So kind of have to be careful with that stuff, especially when you're doing it by hand. But that's, if you want to do a printed circuit board, these are the kinds of questions people ask because, they want to know, are you going to do it through hull or surface mount? And there's a big difference in the production costs when you do things on in a through hull fashion. Not that they can't be automated, they can be. And in fact, there are places here in Connecticut which will automate through hull production. You get a sequence machine, it'll go through a bending machine, they'll make a tape that has all the parts you want on a single tape, and then it'll run it through one board at a time and then go through what's called wave soldering. Wave soldering is the alternative to reflow soldering. With wave soldering, what they do is they set up a standing wave of molten lead and tin. And then they run the boards through the molten lead and tin, and it coats the bottom of the printed circuit board. Then they go and they take the boards through another pass where they cut all the excess leads. And that's what wave soldering does. So here's the standing wave. You can see it here. That's a standing wave of molten hot tin and lead. So this could be 500 degrees or hotter. You do not want to be touching this. And as you roll the printed circuit boards over the standing wave of lead and tin, everything gets soldered. You don't need a stencil, but you do want a solder mask because it'll keep the solder from sticking to things it shouldn't be sticking to. And so, here it is going through the wave, the standing wave. So what they'll be doing is they'll be pumping the molten solder up so it creates that wave, and then it comes down and they pump it up again. And places like this are, I don't know, kind of running a lot of toxic stuff, right? Because the lead will outgas, and lead is, kind of dangerous, and they have to have lots of ventilation, and plus they have to keep the solder hot even when they're not using it. You don't want this stuff to like solidify overnight and then have to reheat it. So this is this is the state of the art for automated manufacturing in the 80s. Nobody was doing surface mount in the 80s. So if you had an Apple II computer made in the 70s and the 80s, that was done with wave soldering. But if you went and got something like a Power PC, something that came in a little bit later than the Quadra computers, then you would have a surface mount, and the whole industry transitioned to surface mount.
Could you do surface mount by hand if you wanted to?
Yeah, absolutely. Yeah, you can
Yeah,
do
the
it.
surface mount NRF board that you saw in class, I did that by hand.
How'd you do that? How'd you heat it up?
The bigger surface mount ones are not as hard as you'd think. There's kind of just a feel to pressing your iron against it. But once they get really little, it gets very tricky.
So when you're dealing with surface mount drag soldering, you can do the very fine stuff. But what you do is you get a beveled tip or a hoofed tip and you fill it with solder, and then you drag it over the leads. So this person is doing drag tip soldering across these tiny little leads. So the kind of surface mount soldering that you did, Chris, isn't the most challenging, I would say. You end up with
Yeah, definitely not. It's not like the little one.
yeah, if you try and do these little guys without bridging the tips, and I know a guy who is excellent at it in Stratford who will do it, you can do that sort of thing without going through a reflow. And here he's dragging the tip and feeding the solder at the same time. It's a bit, it takes a bit of practice. It's a little bit of an art. And sometimes what you do is you tack solder one end, you tack solder the other, and then you drag tip to make sure that the IC doesn't move while you're doing the drag tipping. So that's, yeah, you can solder by hand if you like. You can do the reflow. I've done reflow on a frying pan on the stove. It's you just heat up the frying pan, throw on the boards, and the boards will eventually get hot enough to melt and the solder, and then you take it off. And then if you're using lead solder, it's probably not a good idea to use the pan for food. But the same thing goes for the toaster oven, right? Don't use a toaster oven you care about. Not if you're planning on putting
Toast.
like food in it. It's not a good idea. Get a special toaster just for that. We have a toaster in the stock room, which has been modified to be controlled by a Arduino and has a K-type temperature sensor in the back. So you can use that for surface mount. But also we have a full surface mount assembly line facility right next to the microscope. So with that, you don't actually have to use a toaster oven. You can just throw the boards on one end and they'll come out soldered out the other end. And so you can use the microscope for your pick and place. We've got the tweezers. We've got the surface mount devices. Yeah, you even have a router so that you can route your own printed circuit board off on the corner there. And so, in fact, you can do your whole soup to nuts prototype right there in the shop. So that's actually very convenient. And I do have solder paste, but you want to get fresh if you're going to actually get serious about doing this. And it costs whatever it costs. You don't buy much. A tube like this will make a whole bunch of boards. You're not going to run out of solder paste after you buy a tube like that. And there's a lot of videos on how to do it. And it's a bit of an art. So that's the shtick on surface mount. That's kind of an interesting idea for us to make our own printed circuit boards and such. And I did have a project for one of the classes where everybody was making boards and sending them out, but I don't think we're going to be able to do that here because of how we're handling the end of the semester. Things are they're just happening so fast. And then, what can you do? It is what it is. That's what they say anyway. So you've got the little overview of the Ethernet. You saw some Ethernet code. That was good. I've got another kind of a homework that's been slated for next week. And I wanted to kind of cover that a little bit. And it's about using the serial port with the Arduino. And I kind of think we might want to do something with that. So let's see what we can do with this one. So this is I have a few load cell questions in here, and this gives you a demo of the load cell.
Is homework 10 live?
Is it live? It will be tonight, I think. Let me check.
I don't think it is. I didn't see it.
Tonight. Did I say tonight? Live
Yeah.
tonight. Live tonight. You need it now? I think a lot of people haven't done homework 9 yet.
Yeah, that's okay.
Let me just check. It says will be available after November 12th, 1:53 p.m. So that's today. I guess we could make it sooner. We could make it now.
After class.
Yeah, it's after class. Yeah, we can make it. We can make it available now. Let's see. So then it'll be new next week, and it should say available. Make available. Make available. Yes. 2 attempts and submit. So you should see it now. And so what we'll do is just take a quick look at homework 10 so that we can see a little bit more about load cells and such.
I see it.
So this is a little experiment I did with the load cell. Load cells use a sigma delta analog to digital converter, which gives you a lot of bits but is very slow. And that's being used with a wine bridge, essentially a way to measure resistance from orthogonally mounted strain gauges. And what I'll do is I'll just play this instead of chit chat about it. Okay, I wanted to show you how to wire up the load cell to the standard HX711 board. We're using a standard clock going into pins 2 and 3, and then we have to wire up power to the HX711. Since we're doing pins 2 and 3, we have to make a small modification. Here we're using 2 and 3 for the data out and the serial clock, and so that's what happens when you use the scale begin. Otherwise, what you can do when you want to find the code is you go to File, Examples, and then you're looking for the HX711 master, and this is the standard code. Normally, when you start something like this, it comes out with pins A1 and A0, but I've already reserved those for the serial for the Arduino Audio Shield. So that's why I switched to 2 and 3, so I wouldn't be occupying 0 and 1. When you look at the output of the system over in here, you can kind of see the average, and as I manipulate the load cell, you'll see that it's changing the weight, and I'm pushing it to 19 grams worth of force on the load cell. And so that's my little load cell demo. Hope you liked it. Thank you. Boy. So that is one of those things which I don't think we're going to get to directly here in the in our set of labs. And what we've got in here is let's see, some more examples. I think this is the same. Yeah, 214. That's the same video. We got another PIR video, which is the same video, 412. And I made a recommendation for Tinkercad. And then I've got a demo in here on how to do serial call response for the Arduino. So here we have two-way communication from the desktop computer into the Arduino itself. And then that'll allow us to manipulate things like oscillators and such. Let's see if we can get that one to run. Okay. I'm not going to watch this. It's 23 minutes, and we don't have time for that. I didn't realize how long we've been chit-chatting about surface mount devices. Sorry about that. Essentially, what you want to do is you want to be able to transmit and receive data to and from the serial port. And that is one of those things that requires a little bit of explanation. So far, all of our serial communications has gone in just one direction. So if you're interested in the HX711 and you wonder what kind of an A to D converter it is, you can certainly use the Google to take a quick look. These things are terribly inexpensive. And look, it's a 24-bit high precision dual A to D. 24 bits. How many different levels is that? 2 to the 24. Anybody know? It's like 16 million. So that's, a reasonable amount of bits, but you can't use it for audio. It's good for weighing stuff, but it's really, really slow. So
You're
you
right,
can,
it's 16 million,
yeah, it's sort of done that before. So yeah, it's actually typical to have direct color where you have 8 bits per pixel, red, green, and blue. And so you'll have 24 bits per pixel and 32 bits if you include an alpha plane. And this here is the load cell. And what it does is it allows you to bend elastically up to its safe load limit. And so it says its safe load limit is 150% of the 36 kilograms. So take 36 kilograms, add 18 kilograms, and that's the best you can do before you get to the yield strength of the load cell. Yield strength is the point at which the material ceases to do elastic deformation and then proceeds to do what they call plastic deformation. And that plastic deformation means it doesn't return to its original shape. So in other words, you're deforming it in such a way that it looks really bent. So you don't want to do that with materials like the materials you're using to fly around in your helicopter. And there's going to be a lot of vibration, but you don't want those things to deform permanently. So you want to be able to take the vibration. I just had a helicopter fly overhead because I live across the street from Sikorsky, so they're always flying helicopters. The little white stuff over in here is epoxy, and that's where the strain gauges are going. They got one here, they got one on the underside, they got one on the left, and you'll be able to measure using these little strain gauges. So you fix one end, you move the other, and you will find these in postal scales or in the scales that you stand on, or you can get them in all sizes. They can weigh. If you ever go down a highway and you find a weigh station, they're using load cells to weigh tractor trailers. You go into a junkyard and they've got a little place for train cars to pull up. They're weighing the scrap metal in a train car. So I mean, you can weigh whatever you want, however heavy it is, and you can find a load cell for that. And so that's an important way to sense for the Arduino. In some sense, I guess, weighing a person is like a biomedical signal, right? In fact, people are very concerned about their weight. Yeah. Go ahead.
I was agreeing.
Yeah, that's right. So turns out it all works because of what looks like a very finely created printed circuit board. And what you're doing is you're causing the resistance to change. And you want to measure a small amount of resistance in one direction. And so then these things have been around for quite a long time. And the means of attaching them using, this is, I think, super glue. And it even says so, and it's also known as super glue. You take these devices and you super glue them to whatever, could be the airframe of a helicopter. And, what'll happen is they'll do something like Sikorsky will come out with a new helicopter and they'll say, oh, it's time for a new helicopter for the Army. And they put it on the design board for a decade and it's called Comanche. And then the Army cancels the contract. Meanwhile, Black Hawk is getting very old and they have to keep upgrading its avionics. And it's got a lot of vibration to it. And it's made out of laminates and nobody knows when the complex machines like that are going to fail. So what do? Well, you take your little strain gauges and you use a little super glue and you stick them onto the airframes and check to see if there's any cracks propagating or anything that's going on, like toward the yield strength of the material. Because if it starts to fail, somebody could have a bad day, put it that way. And you want to try and avoid that. So here's electronics from the 1800s, the Wheatstone Bridge, which we still use to this day. And what we're doing there is we're taking one thing that's variable and two other things that are fixed and well known, and we're looking to see if there's a small change in resistance. And so this can be done without a computer. This can be done with a simple galvanometer. And then if you want to put a computer in there, you can certainly do that. And you can solve for one of the unknown resistances, R sub X. And that allows us to essentially measure very tiny changes in resistance. And so here's the strain gauge again. And you can see one part of the flexure goes into compression, where the other part goes under tension. And here we have compression and tension. And we can measure the differences in thickness of the wire, and that changes our resistance. And so that's that would have been a good lab, actually. We could still do that lab, except we're running out of strain gauges and we're running out of time. You guys had a chance to do the PIR sensor lab. I think that was one of our first labs, and I'm glad we did that. And you can probably answer these questions about the PIR sensor with relative ease. You know about LEDs and which end has got the cathode and which one is the anode. This is a schematic of the PIR sensor. I'm not entirely sure I remember us doing this, but you can kind of see this. This is the hot object, the little red dragon, and he's going across the detecting area. And it's that change that the PIR sensor is picking up. And so that change causes this little signal, and it causes a threshold sensor to trip, and you get a digital input. Here's a solid state junction type transistor, which is being used as your PIR sensor input. This is the gate. This is a drain. That's the source. And this is a field effect junction transistor. And one could say the gate works like a garden hose, right? When you have the ability to pinch off the electrons so that they can't flow from the source to the drain, then effectively what you're doing is you're shutting off the flow of electricity. This makes the field effect transistor into a voltage variable resistor, whereas the bipolar junction transistor is a current controlled current source. It's a mistake to simply say a transistor is a switch. It's not. It's an amplifier. And if you operate it in saturation like we normally do in digital design, it acts like a switch. But if you load down a bipolar junction transistor so that it has to drive too many inputs, like more than 10, it will act in funny nonlinear ways. It won't operate in saturation. It won't just go on or off. It'll start to act more like an amplifier. And you have to watch that sort of thing. Now comes the interesting bit. And herein lies the rub. When you create something like a instance of a serial port, you want to be able to store the state of that serial port. And the state of a serial port includes something like what port name is it, right? What's the baud rate, the rate of communication? What's the type of flow control? What is the number of data bits, the number of stop bits, number of parity bits, and where you're going to store all that information. And I like to store it under a thing called preferences. So I have this thing called preferences utils, PU, preferences utils. So what I'll do is I'll give you a quick little demo because we only have 15 seconds to go. And what we'll do is we'll do a thing called the serial port setup. And you can see all of that stuff is here. The port name goes here. Baud rate goes right in here. Flow control is here. Data rate, data bits is here. Flow control is down here at the bottom. and I got the parity. And all of this is going to be stored so that next time I start the program, it will retain the state, and I won't have to reselect things like baud rate and bits and parity and flow control and number of stop bits, which could be 2, 1, or 1.5. And when you test the port for communications, you can hear that the Java program is able to dial the modem, for example. So you can get through voice jail and things like that. So we parameterize an instance of a representation of the serial port in order to be able to retain that state next time your program begins. And this is a critical thing for people who are attempting to use the serial port in order to communicate with their Arduinos, or with anything for that matter. So that's all we have time for today. Here's our little clock. This guy, this homework here, this will be due next week. And what we'll do is we'll come up with an interesting lab, which may end up using the serial port instead of the Ethernet for next week, because I think this may have priority. Serial ports seem to be relatively ubiquitous. So that's all I got for you for today. Thanks for your time. Sorry I went over a little bit, but we're pretty close. Have a good day.